Hello, and welcome to a tutorial about MBX. My name is Henry, and I'm a graduate student in the Paisani lab. MBX stands for Many Body Expansion. This equation is used in our MB energy models, such as MBPol. Today, I will be going over the first tutorial in our series, where I'll talk about compiling and installing MBX on a Linux system. These systems can either be your local workstations or will be representative of what you'll experience on many Linux-based supercomputers. This tutorial focuses on standalone MBX. If you would like to use MBX with LAMPs, we have a separate tutorial for that. All right, let's get into compiling standalone MBX. So on the left here, I have our GitHub open for this repository for the software. And on the right, I'll have the terminal, which I'll be executing the compilation in. In order to get started, definitely scroll down to the README because that will have all the instructions needed to do this compilation. So I've opened up the README and I'm scrolling down to the compilation and installation. To get started, you'll need a somewhat new version of a compiler. It can either be a new compiler, GCC or G++, or depending on your CPU, sometimes you may prefer an Intel-based compiler such as ICPC or ICPX. In the event that you're doing a compilation with LAMPs, you will need MPI, but for this tutorial, we're just going to stick to just an MBX standalone installation involving the G++ compiler. Okay, so scrolling down to setup, the first thing we're going to do is clone this repository. So I'm going to initiate the git clone. This will download the latest version of this repository onto your Linux system, and we will then compile when it's ready. Okay, so if I do an ls, we now see that MBX has been downloaded. I will cd into the directory, and looking inside, we can see that we have the basic source files and other files associated with this repository. Okay. In the instructions, we do have this optional step to export the MBX home, which I will do now. This is useful primarily if you're going to call the executables. You can use this variable MBX home instead of having to type out the whole path. Okay, for this tutorial, we'll be doing a basic installation here, specifically for standalone usage. If you want to instead use MBX with LAMPs, we have a separate tutorial on that. And in that separate tutorial, we'll be instead following these alternative instructions. But we're going to do just the basic installation for right now. Okay. The auto-configure step here is for development purposes. Excellent. And this generates this configure file, which we will now use on this step. Okay, so we're going to do /configure. Do know that we have additional options available depending on what you're specifically trying to do. If you're trying to change the compiler, you would use the cxx directive like this. So by default, it will just pick whatever is in your operating system. But if, for example, you wanted to use the Intel compiler, you can instead specify ICPC or the newer compiler from Intel, ICPX. I'm going to stick with the default that's loaded on my operating system, so I'm not going to include anything for that option. If you want to use MBX with a separate programming language like Python or Julia, you'll need to use the enable shared directive here. Okay, and if you want to see information about the additional configuration options, you can always type configure --help, and it will print everything to the terminal. Okay, so going back to what I was doing, let's just do the regular configure. And the configure will now check your operating system and make sure that you have all the required libraries. Primarily, the main library that you will need, that you may need to install separately, is FFTW, which performs fast Fourier transforms for the PME or particle mesh Ewald part of the calculations. So if you encounter an error, most likely it is you're missing a dependency such as FFTW. Okay, now we're going to actually, since my configure step worked, we're now going to perform the actual compilation. So this will be a make and make install. This compilation should take a significant amount of time, and it also takes up a good amount of memory. So depending on how powerful your computer is, you are allowed to add a higher J value, so it runs more parts of the compile at a time, but do be careful based on how much memory you have. Before we go any further, let's pause for a moment to take a look at how your choice of compiler and choice of J value will affect just how long your compile will take. Before we get into too much data, it's important to keep in mind that your choice of compiler does not really affect the end result. It only affects your compilation speed. G++ is always a good default choice because it will compile the code properly and is quite common on almost all Linux systems. ICPC and ICPX, which are Intel compilers, can compile faster, but they may not always be available. I did some timing tests, and at least on this Intel system I'm testing on, the Intel compilers were up to 4 times as fast as the G++ compilers. Of course, your performance may vary. As you can see, increasing the number of simultaneous jobs or increasing the J value significantly decreases the amount of time needed to compile. However, do note that this will require significantly more RAM or memory in your system to work. As a rule of thumb, we'd recommend taking the amount of RAM you have, divide by 16, and that'll give you a good safe number of jobs you can run simultaneously. Now that we've picked a compiler and a J value that works for our system, we can begin the compile. Since this might take a while, you might want to go get a coffee or something while you wait. So I'll see you when it's done. After quite a lot of time, my MBX compile has finished. So what we're left with, I'll do an ls, is we'll have the executable files here, and depending on your build options, also some stuff in the library. First, let's take a look at this bin folder. So I'm going to cd into bin and do an ls. In the next tutorial, we'll talk more about specifically what all these executables do, but for standalone MBX, the executables will be located in bin, and these do some simple functions that only rely upon MBX. As you can see here, we have mbdcomp, normal modes, optimize, frame ordering, and single point, which is what I personally use the most out of these simple executables. And there's also the IPy driver, which we'll talk about in that separate tutorial in case you want to merge MBX with IPy. Okay, we're going to go back out and take a quick peek in the lib folder. So if you've done just /configure, in here you will see mbx.a and libmbx.la used for static linking of MBX into other codes. If you are thinking of using MBX with Python, and in the previous compile step turned on --enable -shared, MBX will also compile these libmbx.so, these shared objects, which are useful for like Python, Fortran, or Julia code trying to couple with MBX. Okay, and then from our instructions, something you probably should do before using standalone MBX to make sure everything is okay is to do make check. And what make check does is this will run the unit tests and make sure that there are no detectable bugs in this code. So this will take a bit, and then it will run all the unit tests, and we will verify the results. Excellent. The make check passed. All 34 tests successfully passed with no errors. And this confirms to us that as far as these tests are concerned, that MBX seems to have been properly compiled and installed successfully. Thank you for watching this tutorial. Today, we successfully downloaded and compiled MBX on our Linux system. Then, we used make check to verify that MBX is tested and seems to be functioning properly. In the next tutorial, we will actually show you how to use these executables from standalone MBX, as well as how to use MBX with Python. From all of us MB experts over here, we wish you happy simulating.